Okay, good morning, everyone. Uh, Next week we have midterm, right? Next week. So topics will be matrix, system of linear equation, linear algebra, the eigenvalue, eigenvectors, and how to solve the differential equations using eigenvalue, diagonalizations, and one more that I will tell you about today about the you're going to solve both homogeneous and non-homogeneous. We already covered the homogeneous linear equation, how to solve that using a matrix system, using the eigenvalue. And we have different type of eigenvalue. When we have the distinct eigenvalues, we have repeated eigenvalue, and we have the complex. Now, if we have distinct eigenvalue, we can have the diagonalizations. Okay, as long as we have, if we have more than two, as long as we have some eigenvalues that are different, that they are distinct, we can try diagonalizations. But we need to check the matrix P, whether they have the matrix D or not, or whether the matrix D is equal with their eigenvalue or not. And we have done some part of that within this expression here, solving the differential equations through diagonalizations. So they are going to work really well when we can find the independent eigenvectors. Okay, so basically the next part that I will try to cover by today is the non-homogeneous linear system, particularly for the undetermined coefficient method, which we have already covered in Engineering Mathematics 1, but we want to make sure that we can use it in matrix system, in matrix. So we have for non-homogeneous, we have x prime, ax, and for non-homogeneous, we will have another functions. Okay. So far, we solve when we have this only, right? That is when the f of t is a 0. So if you write the f of t is 0, means it is homogeneous. And the expected solution, or the general solution, we are going to have, we call the xc plus xp. If you remember the differential equations, this is the yc and yp. Yp means particular solutions, similar to this one right now, the xp. But the difference is this is already in matrix. Okay, this is in matrix. And the xc, we have shown that from the previous examples, this will consist of several parts of another matrix system until some n, depends on how much we have in the system. So this is we call also complementary. Complementary function, which is the solution for homogeneous system. And the xp, this is a particular solution of non-homogeneous. In the previous examples, when it is homogeneous, we can find the xc, right? We can find the xc. Now we would like to know how to find the particular solution. And within this context, there are actually two methods that is available in the matrix. It can be undetermined, so method. First is using the undetermined coefficient. Basically, undetermined coefficient means that we are going to match the coefficient with the for each part of the variables. And the second is the variation of parameters. But since there are, I think if I put this method, all these two methods, maybe it's too much for the content, so I will just focus more on the first method, okay? We'll cover this, okay? We only cover this. So in the undetermined coefficient, let me write again here. The basis or the principles is we are going to guess, actually, we are going to guess. So making a guess about the form of particular solution. XP. And how we can guess? The guess can be based on type of functions, in the column FT. And let me make this a little bit smaller. Okay. So we are going to have x prime ax plus f of t, and here the matrix A, it will be a constant, right? The entries will be a constant, and for the f of t, the entries can be constant, polynomials, exponent, sines, cosine, or combinations, okay? or combination of, or combination. It can be like product of these functions. It can be finite sums of all of this also. Okay, so maybe let me go through one example, okay, to see how we can match this f of t, okay, with the some assumptions. Okay, now this is the example. So we have this x prime, so this is a, and this is f of t, which is just a constant. So whenever we have the non-homogeneous, what we need to do first is we need to solve the homogeneous, or solve the xc, which means that we solve this, only this part, okay? And how to solve this? Basically, let me write here. To solve this, we need to find eigenvalue, and then well, if it has eigenvectors, we can find the eigenvectors. If it is diagonalizable, we can use diagonalizations. But if not, then depends on eigenvalues. We can have distinct, right? Repeated, or a complex. If it is complex, then we have a template. Actually, we have a template that we can use according to the complex conjugation in the eigenvalues. Okay, if we try to find the eigenvalues of this system, take the determinant, so this will be so +1, right, +1. So the eigenvalues is actually imaginary, it's a complex. So to write the complex notations, remember, we write lambda 1 supposed to be the positive one, and the conjugate, we write exactly the same, but with a bar at the top, which means it's indicating it is its conjugate. This will be negative I. And by the procedures that we have in the previous sections, in the when we have the complex eigenvalue, use complex eigenvalue template. So the alpha is 0 and the beta is 1. Then we can write down the xc, c1, this will be cos t plus sin t, this will be cos t, plus c2 cos t minus sin t minus sin t. Okay. So of course, we need to find the eigenvectors first. I'm skipping that part. So if you don't remember, this is how we can get. Let me write here that the x1 is b1 cosine beta t minus b2 sine beta t e alpha t. X2 will be b2 cosine beta t plus b1 sine beta t e alpha t, and this is for the eigenvalue will be alpha plus I beta. Okay, which means that we need to find the b, which is the eigenvectors. Let me maybe write here just to review of what we have learned before. So b1 is actually b1, we can write this is the real, which is the k1, and then b2 is the imaginary of the k1. So the eigenvectors we are going to split becomes the real part of eigenvectors and the imaginary parts. Okay. The real part we say it's at b1, and the imaginary part will be the b2. Okay. Now after we get this, which means we solve for the homogeneous part, right? And since this is the, if we see the f, if we see the f, which is having just a number there, here, the f here, this f means that this is a constant, right? This is a constant. So if you remember what we did for constant when we have that constant in our equation, in differential equations, the particular solution will be another constant, right? Will be another constant. So we can guess and try to make up that constant with just notations like A, B, or other notations. So we can assume, since f of the is a constant vector, assume that the xp is having b1 and y, a1 and b1, which we can substitute to the original system. So let's substitute this, meaning we can substitute all this column vector with each one of the matrix X. Okay. So next is substitute xp equal a1 b1 into original equation. Original equations, let me write again here, is, let me just make it smaller. So x prime okay, this is the original equation. So we can substitute the a1, b1 to the x. So substitute here into that one. So minus a1 plus 2b1 minus 8, and this will be minus a1 plus b1 plus 3. And suppose that this will be solving this equation, which is this will be equal to 0. And then we can solve this linear system. So we can probably subtract. So b1 is negative 11, or 11 if we put on the right side. And A1 will be 14, right? 14. And so this is our particular solution. So when we have xp equal 1411 factor, this will give satisfaction in the solution. So general solution on the whole interval will be xc plus xp, or we need to write all the combinations between those two. So cosine t plus sine t cosine t plus c2 cos t minus sine t minus sine t, and then plus 1411. So basically, most of the system will be depending on the f. Okay. So whenever we have f, it can be a constant, it can be exponential, it can be just a regular linear system, or maybe parabola, but probably linear. And I think for our case, it could be either constant, linear, and a exponent, I think. And some perhaps parabola, and well, a simple trigonometry could be also. I think we can have more examples later on. Okay, so now let's see the wait. Let me mark this some idea here. Solve the xp, and then finally get the product general solution. Okay. Okay, the next part will be another example. So here's another example. Now it's a linear equations. Okay? Now linear equations. So here's the f of t. This is the a. Right? F of t now is the linear system or linear equation. Okay, as usual, we start with the solve the homogeneous. So finding the determinants. So we have lambda can be factorized 2 and 7. So there's distinct eigenvalue. So distinct and then so solve eigenvalues. Solve eigenvectors, which we get the eigenvectors for lambda equal to, this will be 4k1 plus k2 equals 0, 4k1 plus k2 equals 0. So k2 is negative 4k1. So suppose that we can make k2, or let k1 is 1, then k2 is negative 4. So we can have some possibility for eigenvectors 1. It can be 1, negative 4. And for lambda 2, which is 7, this will be negative 1. So negative k1. 3 minus 7 is minus 4. So k1 is k2, which means that this is for sure, this will be 1, 1. So k2 is 1, 1. So complementary functions will be 1, negative 4. This is for the eigenvalue 2t. And then the second part, the eigenvectors 1, 1. This will be with the 7. So, and then, so this is, we get xc, and then 4, solve xp. So since f of t is, we can split this f of t, become 2 column vector. This will be 6, negative 10t, and then another part will be a constant, right? So based on this structure, we can assume, so assuming that the xp, this will relate to this structure, which is a constant here, t, and then how we name the A1, B1, it's up to you, basically. This is, for me, I will always start the constant as A1, B1 for the column vectors. And then this one, substitute into original equation. Which means that since it has a linear equations, we can derive to make it xp prime, that this will be a1 or a2 b2, and the rest will be 0. So substitute all of this. So not only the xp, but the differentials also. So we are going to have, I think I will write here, this will be xp prime a xp plus f of t. So xp prime will be a2 b2, a will be 6 1 4 3, and then the xp will be a2 b2 t plus a1 b1, and then plus 6 negative 10 t plus 0 4. Okay, now we have this system, and then solve it, make it into a system of linear equations, and we are going to have a four variables that we need to solve. So we can try row operations if you like, but I think if it is simple enough, we can try just a regular method, just substitutions, eliminations, substitution, eliminations, and then we get a1 b1 a2 b2. Okay, and then solve. So I think we'll start from here. Let me combine, I will split, become t. Oh, why I'm doing this? I think I will just directly multiply, sorry. So 6 a2 b2 t Okay. And then in each component we are going to group all the variable t with variable t and all the constant with the constants. So this will be 6a2 plus b2 plus 6, 4a2 plus 3b2 minus 10, right? And then plus let me put here this will be 6a1 plus b1 minus a2, 4a1 plus 3b1 plus 4 minus b2. This will be equal to 0. So we can look at the system now. That we have four system. Okay, so 4 equations, okay, in this system. So first we can have 6a2 plus b2 plus 6 equals 0, and then 4a2 plus 3b2 negative 10 equals 0. And I think we can solve this too to find a2 and b2, right? And then when we get a2, b2, we can substitute to a1, b1, and we get that a1, b1, right? Okay. So I will multiply by 3 and then subtract. So this will be 14a2 18 minus 10 is 8. Four plus 3 supposed to be 8. So a2 will be 4/7. Is there any 6/3 is 18, right? 18. Yeah, should be correct, right? And then we can substitute to get the b2. So 6/7 plus b2 equals -6. So b2 is -6, -24/7. negative 6 over 7. I think the number is not good. Hmm. 4, 3, but I think it's correct, right? Is there any, can you find any mistake here? But anyway, the idea is just to find the A1, A2, B1, and B2. So this is A2, B2, and then substitute this A2, B2 to the next equations, which gives you 6A1 plus B1 minus 4 over 7 and then 4A1 plus 3B1 plus 4 minus plus 66 over 7. Now suppose that we have A1, okay, and B1. I think this is a bad example. Not really good number, but can you find any mistake here? I think maybe I'm having a mistake, but I don't think, if I see this, I think I'm in the right way, right? All the, huh? Mm-hmm. Which one? Uh-huh. Ah, good. That's why it feels so weird. Good. Good. Now it's better. Yeah, minus. Yeah, it's plus. Correct. So 6, 2. Oh yeah. Right. Here, right? Okay. So this will be negative 12. So B2 will be plus 12 minus 6, which is giving you 6. This is better. And then substitute back to this part. Okay, this will be minus, so minus 2. And this will be 4 and minus 6. I think the same way we can make, let me rewrite again, 6A1 plus B1 plus 2. Or maybe let me just put into the right side. This will be negative 2, so 2, right? I will multiply by 3 and then minus. Okay, we can have a break for a while. Okay, so let's just continue just to write the general equations for the solutions. So we already have all A1, B1, A2, B2. Okay. According to what we have in this structure, then we are going to exchange this A1 and B1, A2, B2 according to our assumptions. So we assume the A2, B2 is for variable t, A1, B1 is for the constant. So we can substitute back to the system and write the whole thing. So we write the x is xc plus xp. So xc will be c1. Okay, and then we have the A2, B2 is negative 2 and 6. So this is negative 2, 6, t, and then plus This will be negative 4 over 7. This is 10 over 7. And this will be the general solution. So the general solution. So 5 get x. Okay, so basically, how to assume the xp is based on the function f in the system. If the f is a constant, then the assumption will be a constant. If the f is a linear equation, then the assumption will be linear equations, and so on and so forth. Then if it is maybe sine or cosine, then our assumption will be also sine and cosine. Just similar to what we have in engineering mathematics 1. And also, as a remark, if, for example, if the xp assumptions, if they are going to have the same component as the xc in the homogeneous solutions, then we need to multiply the xp so that it is linear independent. Okay, I will maybe later I will write for that. Okay. For example, now it's okay because we have all values for the eigenvalues. It is positive eigenvalues, right? So no problem. And if it is negative, also no problem. Because all of them, they are linear independent. Okay. But the problem would be, for example, if maybe one of them 0. If they are 0, this is 1, right? So this is having a constant, right? Having a constant. So this might cause a problem. So we need to make sure that it is linear independent. So if that's happened, then we can try to find, like in the engineering math 1, we can multiply the multiplication of t for several times. For example, if it's become t, we can multiply with the e with t with power of 2t, and then if still happens, multiply again t squared. Okay, so until we can make sure that all of the components are linearly independent. Okay. So the best way to see this problem is so if we have later here, so if we have for example the x dt, not in the matrix form, so that we can see clearly. Okay. So if we see from this part, we are going to see that this part and this part, this will be our f, right? This will be our f. So we can write the f of t is -2, 1, and we can make each one of them. No t in the first one, so 0, and -5 for t, and then plus, this is the constant, 1 and 7. So a natural assumption for this part, so xp, it's better to be the same structure with all of this, right? So let me start with 3. But anyway, to name the A1, A2, A3 is up to you actually, but I will start with the highest one for the exponential here. And then A2, B2 for t, and then the constant will be A1, B1. So using this, and then we can have a good expressions. And to substitute, we need to make it into the xp prime. So we have to solve the its derivative, and then substitute back, and then we solve for A1, B2, B, and then the A3 as well. So we get everything, and we get the general solutions. Okay. Now, as a remarks, I would like just to mention what I told you before. If f of t contains or if f of t is a constant factor and the eigenvalue is 0, and this is multiplicity of 1, suppose, if, okay, then the homogeneous part, the xc, it contains a constant factor, right? And if we see the multiplication rule that we would like to try the xp that is in terms of this, which is not a proper solution. It should be xp or A2, B2, sorry. And similarly, if this example here, if we exchange the, if we replace e with power of negative t, okay, with e with power of 2t, and of course this is 2 is eigenvalue, where eigenvalue is equal to, then this is cause a problem. Okay, cause a problem. The correct form so we are going to have t e to t plus, so we are going to have this is e to t plus a2 b2 t and then a1 b1. Okay, this is if this happened. Okay. So for example, since the eigenvalue is 2, so let me start with the original equation. This is the original equation, and we have the xc, which has the e to the power of 2t. Now, if we change this, change the question, and then this is having the 2t, this will have the same groups with the homogeneous. So this will be 2t. Homogeneous will have 2t also. But this will be a problem because they are supposedly linear independent, right? So what we could do is we need to add one more component that should be linear independent. And if you remember the engineering mathematics 1, what we need is just to multiply with t, and this will solve So this could help us to solve. So we need to add this component, and then we have another component, which is this is component from here that is going to connect with the xc. Okay. So and then we have another component for t and for constant. Okay. So this is additional components that we need to add. So this is additional component. Then using this component, take derivative and then substitute back to the system. Okay, that is for some exception. Okay? Whenever so be careful on the particular solutions. We need to make sure that it is linearly independent and check the eigenvalues. Check the eigenvalues. So that is undetermined coefficients. And I think I need one more small topics to finish off of this topics for the non-homogeneous system. So since we already know the diagonalization, so let's use that as well to solve the system. So we already have using the diagonalization to solve the homogeneous system. So now we try to solve the non-homogeneous using diagonalization. So let me go into the, here is the diagonalization in non-homogeneous. So we are going to diagonalize the system x prime equal ax plus f. And suppose P is matrix that satisfy P inverse A, P equal the diagonal matrix. This is diagonal matrix. And then substitute the x equal py. Okay, we introduce y within this into so we substitute x. This will gives you, so this will be x prime py prime. Okay, so we can substitute all into the system. This will give py prime apy, and then we have f. Okay, let me just write f of t as f. And then multiply with the p inverse on the left, so we can cancel p. Or since this is d, so we can write that this will be y prime dy plus let's say this P inverse F becomes a new function G. We name a new function G, so plus G, where G is P inverse F. So this is a column vector. So each of this differential equation in this new system becomes yi prime is lambda I this from the dy, and then plus gi of t, where I can be 1, 2, and more until n. So if you remember the diagonalizations that we did before, we just need to find the matrix P without confirming whether it is going to diagonalize directly or not. But now we need to also to compute the P inverse, okay? Because the P inverse is needed to be multiplied by F to find the new column vector G. Okay. So we need to find P inverse and G. The procedure will be as usual. We start by taking the eigenvectors, which we can arrange the matrix P and substitute this P into Py, and then we can solve the system. Let me write on the right side here to give you a clear result. Okay, so suppose that we have this example here. Solve the x prime equal 4221x plus 3e power t et by diagonalizations. So first, as usual, we find the eigenvalue. So this will be lambda squared minus lambda minus 4 lambda is minus 5 lambda. 4 minus 4 is 0, right? This is 0. So lambda is 0 and 5. And then arrange the eigenvectors and arrange the P. So for lambda 1 equals 0, think we can agree that this will be minus 2k1. So we can see that this is the ratio k1, k2 is 1, negative 2, right? So we can have k1 is and this is 1, 2 without negative, and we see that it should be 2, 1 now, right? K2 is 2, 1. And then we can arrange a matrix P, so matrix P. So P will be 1, negative 2, 2, 1. And find the inverse of this P inverse, matrix P and P inverse. The P inverse will be 1 over determinant. Determinant will be negative 5. One minus 4, minus 4, plus, right? Plus 1 over 5. And then I will take this just 1, 1, still the same. This would be negative 2, 2, right? Or if you want to combine all together, this is supposed to be okay. So that's just the P inverse. And then find G, which is the P inverse F. So G will be 1 over 5, 2 over 5, multiply with F is this, right? This is F. So 3 ET, and then ET. So 3 over 5 minus 2, it will be 1 over 5. So 1 over 5 ET, and 6 over 5 plus 1, so 7 over 5 ET. So this G will be going to be this. Okay, so what we are going to do is we need to make this y prime. Okay. So let me making a little bit smaller. So G is that, and then let me write here our D. So use and then we have uncoupled system. Uncoupled system is the y prime equal py, or d is, we already have multiplied with the p inverse, so become dy plus g. And remember, d is diagonal matrix, which is the diagonal eigenvalue matrix. Okay. In our case, since our eigenvalue is 0 and 5, we can write here the D is 0, 5, 0, 0. Right, that's our D based on this eigenvalues. So we can put everything into the equations. So y prime 0, 0, 0, 5 plus this 1 over 5 and 7 over 5e. Okay, now we solve this first, okay? And then after we solve the y, we get back to the x, which is the x is py, okay? Remember that x is py. X is py. So solve the y prime. Then we can solve through the equations here. Oh, sorry. I forgot the y here. Okay. So y1 and y2 we have. So y1 prime, since the y is multiplied by 0, it's gone. So only have a constant 1 over 5e with power of t. And y2 prime is 5 y2 plus 7 over 5e power of t. And then solve the differential equations. We can use many methods. I think we can use the undetermined coefficient here, which gives you, for the first one, I think we can try each one of them. We tried solving one by one. This will give you y1 is 1 over 5e t plus c1, and y2 is negative 7 over 20e with power of t plus c2 e 5t. and then the end we are going to add the x is py, so py will be 1, so x is py. So p is 1, -2 to 1, multiply with all this y, and then we can solve this. Okay. Okay. Okay, let me check. Okay, I think we can have a overview. Okay, so this is some of the examples for the undetermined coefficients. So I think we can try to look at, especially I think I will try to look at the I think we haven't seen the trigonometry, so let me just go through number 6. Okay, and you can try the other question as well for this undetermined coefficients. So for example, if we try number 6, this will be our f, right? This will be our f. And as usual, we start by taking the eigenvalues. So we get the determinant. So -1, negative lambda. Plus 5. And this will be lambda squared minus lambda plus lambda 0, so plus 5, right? Oh, no, 4, right? Okay, this is equal 0, so lambda squared is -4, which gives you, this should be a complex. And then from this 2 eigenvalue, we can have a k1, which is 5, and then 1 plus 2i. Why I'm writing this should be factor. And then k2, 5 and 1 minus 2i. Okay, so eigenvalue, and then this is find k. And third one, we get the xc, which is a template complex, is 5 cosine 2t, cosine b, right? Cosine beta. This will be cosine 2t minus 2 sine 2t plus c2 5 sine 2t 2 cosine 2t plus sine 2t. Okay, so we get xc, and then since we have the f of the is this, so let me write here. Remember, the best way to take assumption for xp for this trigonometric is by a sine and a cosine, right? So we can take this as the first one is with the group which has the cosine, and then the second one will be group which has the sine. Of course, we can also try to take derivative to get into the system. And by these two, we can substitute sub to original equation. And I think this is not a problem because the XC is the angle is 2t, but now we have t, so I think should be okay. And you have a system of linear equation that you need to solve, and then finding the last part will be finding the a1, b1, a2, b2. So we can write that this is supposed to be, I will just write the long equation, but you need to try to find a1, b1, a2, b2. Okay. This will be equal to the -1, 5, 1, and the x is okay, and then plus the f. F is sine t minus 2 cosine t. And what's next? What's next is we group all the terms, and we group but based on the sine and cosine. Okay, so we are going to have some equations. So we are going to have 4 equations. And finally, we can write the general solutions if we get the A1, B1, A2, B2. Okay. Okay, I think I will end up until here. I think you can try to solve that. Solve this one. Basically, you need to do all the terms. So we have these equations and that equation. So next week, don't forget we have a midterm. Okay, please come.